This is the events discussion for the week of 3/4 to 3/8. I'm going to talk about three events. One is a presentation in the StorageX seminar, which is about lithium metal batteries, actually. And I want to use this opportunity to dig a little bit deeper into the battery technology efforts here at Stanford, because I think I'm neglecting it a bit. So Wenbo Zhang, he's a 550 PhD talking about lithium metal batteries, in particular some methodologies in how to improve the supervision of the battery. So if you want to improve the performance of a battery, you have to first be able to detect what's wrong and then fix it. So this in this particular case, we're talking about so-called SEI layers that inhibit the battery. So there are some processes and technologies that can be used to improve that layer's inhibitance in order to reduce it. To reduce the inhibitance by actually discharge resting the battery. In other words, you discharge it and you rest it for a while, and then SCI layers dissolve, and then lithium can connect back to the electrolyte and do what it's supposed to do. That's kind of the idea. Professor Kui's group, of which Wenbo Zhang is part of, works on other technologies. I'm going to talk about this in more detail. The second presentation we want to talk about is towards hybrid event image vision. Dr. Andreas Suess, this is semiconductor-based technology that has sort of neuromorphic characteristics. In other words, it can detect something and then operate on it, or if it doesn't detect, it doesn't operate, so you can have lower power, higher performance solutions. And third, reinforcement learning for better human performance. So this is the inverse of reinforcement learning with human feedback. This is, if you will, reinforcement learning with machine feedback to improve human performance. This is not even on podcast. It's March 9, 2024. This is Crimdelco. For the year, we are down 17.8%. The market is up 7.5%. We're underperforming by 25.3%. The first presentation I want to talk about is Wenbo Zhang. He's a 50th PhD here at Stanford in material science. And the idea is really to do research on lithium metal batteries. What are lithium metal batteries? Those are batteries that don't use as a cathode. They don't use lithium compounds such as lithium phosphate, lithium cobalt. They use just lithium metal. This is better, higher energy density. However, the lithium metal degrades. There is certain problems with dendrite formation, and then there's the problem of SEI, a layer formation that isolates lithium metals during charge discharge, and then makes it basically less effective, gives it less or reduces the specific energy, and therefore it reduces the Coulomb efficiency. Coulomb efficiency is what you put in and what you get out. So if you put in 100 units of energy into the battery and you get 100% 100 units out, then you have a Coulomb efficiency of 1. And if that output is less than what you put in, then it's less. So why is it less? Because you have this degradation. So think of it like that. You put in some energy, you put in electrons into the battery, but they somehow get lost. They get trapped somewhere. They can't be recovered, and that leads to a degradation. If just in general, I want to use this presentation as an opportunity to talk in general about the material science effort that I think we at Orange Capital Partners are a little bit underestimating this, because we're so taken by AI, and it is definitely a big part of our valuation and our performance as far as Tesla and NVIDIA are concerned. But there is the part of material science, in particular battery technology, which is incredibly important for Tesla. Let's not underestimate this. We are still working on higher energy density, higher power density. We're thinking about new technologies, new battery technologies, and in particular also scaling. And I think this is a good reminder that there's a lot of work in the lab which can or cannot help scaling up decarbonized energy infrastructure. Let's if we think about Battery Day and in general the idea of decarbonizing the energy infrastructure, we remember hopefully that certainly it's about transportation, and for transportation we need battery technology. It's about utilities. We need battery technology to bridge the gap in intermittent renewable energies. And then we also have other technologies such as heat pumps and things along those lines. But when it comes to energy storage, the fundamental problems are energy density, power density, degradation, cycle time, and then cost and scaling. And I think on all these factors, of course, Tesla is certainly a leader by a long shot. I mean, it's fair to say that maybe some of the Chinese manufacturers are certainly on their heels, but when it comes to scaling and when it comes to particularly capital efficient scaling, the Chinese manufacturers are probably not as good because we have the issue of capital not being scarce. So what all this means is that you could have, let's say, a good performance of a lithium metal battery in the lab. Doesn't mean that, and you could even have a good recovery of some of the performance losses, let's say through, charge resting. So which means you can discharge the battery and rest it for a while and recover some of it. But is this going to scale to millions and millions of cars, millions and millions of stationary storage? Those are always the questions. And I think recently, actually, J.B. Straubel gave a presentation here at the Environmental Sustainable program. They had an invited talk, and J.B. they spoke about scaling. And, just as a tangent, for us, scaling is some of the most important ingredients in wealth creation is actually scaling. So we discussed this in many different versions. We spoke about iteration, disruption. The mission of this fund is to invest in fundamentally new concepts and engineering practices with large impact, which requires, of course, iteration, try and error, but it also requires scaling. And scaling is mainly driven by risk-taking. So scaling and risk are almost the same, two sides of the same coin, because very often scaling is associated with risk. And the reason scaling fails so often is because there is a lack of risk-taking, sometimes understandable, sometimes maybe less understandable, but most people are really concerned about their careers when they work in the workplace. And taking a risk which involves scaling often puts that career, at least, maybe not on the line, but it puts it at risk. You're much better off with incremental steps than with big steps that could, cost you the farm. And some companies like Google have recognized this long time ago when they said you have to break things and all of that. The problem that they did it with other people's money, whether it's their own money that they earned through a monopoly, which is kind of like other people's money. See, money wasn't scarce, and therefore it doesn't count. When it counts, if you really want to scale something, you have to take a risk in a way that the project and your career and maybe even your livelihood could be at risk. That's when things scale. The reason that's so important is because money has to be scarce, and that's how you get the persistence which is necessary to execute on scale. Like you can be a scientist in the lab, you can try to do research, find solutions, but scaling is often related to persistence. It's kind of like swimming from Cuba to Miami, or climbing up a really steep hill, or something like that. You need the persistence to scale something up, and that's why money needs to be scarce. That's why companies like Google cannot scale beyond of course their initial business, which they scaled, and that's why they're so successful. And all the kudos to them. What I'm talking about here is not criticizing Google's business. It's a great business, makes a lot of money. It's the ability to scale other projects which require the scarcity of money in order to have the persistence which is necessary to scale. You take the production, for example, of a car. A little bit more of the material, which cost me a little bit more, but then I reduce the long-term service requirements. It could be cheaper to build the car that way. So there's a lot of these types of things. Scaling is a multimodal moving target that certainly doesn't have, I don't think it converges. There's no solution that converges. It's a moving target. It's more of a reinforcement learning type problem where you kind of approximate the optimal solution, but you will never have really an optimal solution because everything changes all the time. So back to Wenbo Zhang and Professor Kui's group. So what Professor Kui is working on in general is better materials for battery technology. So for example, nanostructures for anodes. So the anode in a lithium-ion battery is graphite. Maybe we can have some two-dimensional or even one-dimensional graphene or graphite that has very different characteristics and could potentially massively improve the performance. So there's some material science research on that front. Another really, really important thing is sort of the relaxation and stress, characteristics, facile strain relaxation. So when you charge and discharge a battery, some of the lithium, for example, it strains, it breaks, it's frickle, it corrodes, like a lot of these things. And when we talk about material science in general, what we talk about is we have to first detect stuff. We have to even see what we're trying to, we have to see things, and then we try to fix them. It's very difficult to fix a battery if you don't see what the problem is. So a lot of the technologies are in that realm. The next presentation I'm going to talk about is Dr. Andreas Suess. He's with Omnivision. It's a chip company. I've never heard of them actually, so that's interesting in its own. Towards hybrid event image vision. So what this company is trying to do is two things. One, it's trying to build event-based sensing, which uses smart pixels that create events upon changes of light intensity. So using luminance as an indicator for events. Once you have an indication that something's changing based on the change of light intensity, you can then activate a vision sensor. So what Andreas is doing is really two things here. One is he's creating an event-driven or neuromorphic chip that is smart enough to activate itself whenever there's an event. And then second, he's integrating this event-driven chip with a traditional CIS device, which is a CMOS image sensor. So that I think of that like that's an image sensor that continuously is consuming luminance and creating or processing that information into a potential algorithm that could then recreate the image, detect the image. And what the event-driven or what event-based vision sensor does, it activates the CIS only when there is an event. So that is, it does, on the one hand, lower power consumption and also lowers compute and memory budget and all of the things that are incredibly crucial for edge computing. I think in Suess's or Andreas Suess's presentation, a couple of things came to my attention. One, they spend a lot of time measuring whether their event-based sensors actually work. And that is based on simulation, that is based on predicting certain things. So let's say you have an event-based chip that is supposed to detect certain luminance, and you want to make sure that when those luminance are present, it actually detects them. So you have to create an apparatus that can simulate a control environment so you can actually check if your chip is really doing what it's supposed to do. So Andreas spent quite a bit of time talking about that. And since this is an engineering seminar, it makes a lot of sense, right? You can't just tell me I have a chip that is able to detect events based on luminance and then kind of let me believe that you're right? I want to see it, and that's what he did. And then the next step is, once I have a chip that works, how do I integrate this into existing CMOS technology so I can save time and space and money while producing it? Lastly, I want to mention that Andreas's main target is to create use cases for this, and we could see use cases, things like GoPro or slow motion, where you have, let's say, if you want to take a picture of a bullet that goes through the air, you would use an event-driven CMOS system where you don't continuously process the empty air, you only process when the chip, when the bullet goes through. So those are the kinds of use cases. I think this is interesting, again, from an engineering perspective and an application perspective, because it shows you that there are potential solutions to very difficult problems that could be also in the chip design. So this could be done algorithmically, of course. You can have an event-driven algorithm that detects something and only then processes the information, but this is a chip-driven or hardware-driven solution to the event detection problem. Last presentation I want to talk about today is Park Sinchaisri. I might be butchering his name. He's from the University of California, Berkeley Haas School, and the paper he presented is Improving Human Sequential Decision-Making with Reinforcement Learning. So I like this for two main reasons. One is this is the inverse of reinforcement learning with human feedback, where instead of trying to improve the machine by giving it human feedback, you're trying to improve the human by giving it a machine feedback. What does that mean? It means that you're doing reinforcement learning, offline reinforcement learning probably. Let's talk about the actual algorithms used a bit later. Let's talk in general. So using reinforcement learning to learn the optimal trajectory of action. So for example, barista making espresso. You take one barista and she makes the espresso, and yeah, there's probably an optimal trajectory of how she can make that espresso in that particular bar. Use 10,000 bars with 10,000 baristas and find the distribution of optimal espressos. You might actually find a trajectory that no individual barista can have. Weigh the coffee a little bit more, give it a little bit more temperature, or whatever it may be, right? The problem here is we're trying to do variational inference from a distribution that is very large and very diverse, and then we try to find the path towards the most optimal solution. Now, how do we do that? Whether we do that with on or off policy, with model or non-model based RL, with deep learning or non-deep learning, that came a little bit short in the presentation. I think Park kept it short because I don't think he's very versed in actual reinforcement learning algorithmic research, which works better. But nevertheless, I think it was interesting to see the concept, right? The concept, again, you use a distribution of trajectories of human skills, whether it's making coffee or whether it's painting a painting or lots of skills, maybe more blue-collar type skills, but we could actually extend this to any kind of skill. And I think the second point I want to make here, which is really interesting, is that you could also look at a recommendation engine, for example, Netflix, as a similar situation where this is a game that Netflix is playing, or excuse me, the user of Netflix is playing a game, and the game between Netflix and the user is to keep the user engaged. That means to not have the user cancel the service. And the game is done by giving the user tips of what to do and how to not go to another website or not, watch another movie and so on and so forth. So in that sense, I think every recommendation engine or any kind of statistical inference that we can use from data to make recommendations to humans can be viewed in that same realm. So this is not just about giving tips for baristas making coffee. This is in general, whenever a machine is interacting with a human, you could use variational inference from a large distribution of data and distributions of that data to help the human navigate. You could think of the self-driving car problem as a game between the car and the human, with the goal that the human never engages with the car and is happy. Maybe you can have a couple of rewards. One is not don't engage. The second is be happy. And you could think of the Netflix recommendation engine like that. And you could think of a barista enhancement engine, which makes better baristas. You could think of it like, again, any kind of interaction between a machine and a human could be enhanced by the machine using machine learning, which is just another word for having a large amount of trajectories for that specific task, that specific event, and then use the best trajectory. Now, I mentioned I'm going to talk a little bit about the algorithms used. So in the case of Park's method, he's using reinforcement learning, and we just spoke about reinforcement learning in one of the previous episodes when we spoke about Vladan in particular using reinforcement learning, deep reinforcement learning, model-free on-policy deep reinforcement learning for the drone problem. And in that sense, we could discuss which kind of algorithms would be better or worse in which scenario. And I think in general, I have a feeling, this is just my gut feeling, that this model-free on-policy deep reinforcement learning actually, to me, is the best solution, in particular, if we can have better simulated environments. If we don't have simulation, then the on-policy thing and the model-free thing might not work, so we might have to have the inverse. We might have a model-based off-policy type reinforcement learning algorithm, because then, the problem is if you don't have simulation, then you're looking at a situation where mistakes are costly, and you want to make sure that those mistakes can then be reduced with a model. And you want to have off policy in the sense that you don't adjust the policy right away, because that could cost you something. So I think in terms of what algorithms to use, there's a lot of research to be done. People like Sergey Levin and others are, I would say, leaders in that area, DeepMind with their work. There's a lot of resources out there also for what reinforcement learning algorithms to use. But I think in general, Park's presentation just inspired me to think about almost every problem in the world where machines can be used to enhance human activity is, in a nutshell, the problem of, or the ability to use a large distribution of trajectories, find the optimal distribution, and then help the human take advantage of that knowledge. Thank you.